Welcome to today's deep dive. Usually when you think about sending a package across the country, you focus on the logistics, the trucks, the airplanes.
The physical movement of it.
Exactly. You drop a box in the mail, and the Postal Service promises they'll route it to the right city. But here's the thing about the Postal Service. They don't necessarily care if the fragile vase inside that box gets smashed to pieces along the way.
Yeah, or if they drop it on the curb instead of, handing it directly to the person who actually needs it.
Right. They just move the box. And that's actually our starting point today.
Which is a perfect visualization for how the foundational layer of the internet operates, because the Internet Protocol, or IP, it handles the routing. But the actual condition, the sequencing, the reliable delivery of that data...
That's somebody else's job.
Exactly. That is a completely different engineering problem.
And it's an engineering problem being solved inside your computer right at this very second. We're opening up a set of technical notes today titled Module 14, Transport Layer.
Sounds very academic.
It does. And if you're listening and wondering why we're dedicating a whole deep dive to a single networking module, just stick with me. By the end of this, you're going to understand the invisible, perfectly choreographed ballet that happens inside your devices every single time you send an email, stream a video, or just browse a web page.
It really is a ballet. The transport layer is kind of the unsung workhorse of the internet because, most people are familiar with IP addresses.
Sure, yeah. We hear about IP all the time.
Right. And as we established, IP is like the postal network. It's entirely focused on getting packets of data from one side of the globe to the other. But IP is inherently careless.
Careless.
Yeah, it's what network engineers call a best effort delivery system, which is really just a polite way of saying it offers zero guarantees. It never manages reliability or specifies how the delivery actually happens once it reaches the destination machine.
So that's where the transport layer steps in, right? It sits right on top of IP in the networking stack. It acts as this crucial link between the software applications you're actually using, like your web browser, and the raw physical network hardware down below.
Yeah. And consider the gap between those two things. An application generates a block of data, say a high-resolution photograph you want to upload. The application doesn't know anything about network cables or fiber optics or packet sizes.
It just has a giant chunk of data.
Exactly. But the physical network, on the other hand, can only transmit tiny sequences of ones and zeros. So the transport layer has to step in as the intermediary to translate the application's intent into network reality.
And the notes break down this intermediary role into a few core responsibilities. The first one is segmenting data, which makes sense because you obviously can't shove a massive 4K video file through a network cable all at once.
No, definitely not. It would completely clog the pipe.
Right. So the transport layer slices that massive file into tiny, manageable segments that conform to the network size limits, sends them across the wire, and then, and this is the crazy part, takes on the monumental task of reassembling them in the exact right order at the destination.
Yeah, and while it's doing all that slicing and reassembling, it also has to track the conversations and handle multiplexing.
Okay, multiplexing. That is one of those words that sounds incredibly dense, but the mechanism is fascinating. It's essentially the operating system's way of untangling a massive knot of data.
That's a good way to put it.
Think about it like a busy restaurant kitchen. You have multiple orders or conversations coming in all at once. The transport layer is the expediter. It has to make sure the fries don't end up on the dessert plate,
I love that analogy because think of the network cable coming into your computer as just a single pipe. Every piece of data from the internet flows through that one pipe. But on your screen, you might have 10 browser tabs open, a Spotify music stream playing, and a file downloading in the background.
Yeah, and they're all happening at the exact same time.
Right. If the transport layer wasn't multiplexing, your computer wouldn't know how to separate that incoming stream of ones and zeros. You'd end up with a line of HTML code from a web page accidentally playing through your audio speakers as static.
Oh, wow. Yeah, that would be a mess.
Mm-hmm.
So how does it actually untangle the knot? Under the hood, the transport layer takes the incoming data from that single network pipe and maps it directly to specific process IDs running in your computer's RAM.
Mm-hmm. It's constantly switching context, threading a few bytes to the browser, a few bytes to Spotify, back and forth. It interleaves these streams so flawlessly that it creates the illusion of simultaneous parallel communication.
And to manage all of that interleaving, the transport layer relies on specific rule sets or protocols.
Sure.
But it doesn't force a one-size-fits-all solution, right?
No, not at all. The architects of the internet recognized early on that different applications have drastically different requirements for how data should be handled. So they gave developers a choice between two primary protocols, TCP and UDP.
Okay, let's start with PCP, the Transmission Control Protocol. If we go back to our mail analogy from earlier, TCP is the highly insured, registered letter of the internet. It absolutely demands a signature at every single step.
It really does. It is the definition of a connection-oriented, highly reliable, full-featured protocol. When an application uses TCP, the transport layer is essentially making an ironclad guarantee.
Which is?
It guarantees that every single segment of data sent by the source will arrive at the destination uncorrupted and in the correct order.
The mechanism behind that guarantee is intense. The source material outlines 4 specific services TCP provides. First, it tracks and sequences. Every single byte of data TCP sends is assigned a specific sequence number.
Right, because IP routing is dynamic. Packet number 5 might take a fiber optic cable under the Atlantic, while packet number 6 gets routed through a satellite and somehow arrives first.
Exactly. So TCP looks at those sequence numbers, holds packet 6 in a temporary buffer, waits for packet 5, and reorganizes them before handing the data up to the application.
It's meticulous. And second, it demands acknowledgments. It doesn't just assume the data arrived. When the receiving computer gets the data, it's actually required to send a message back to the source saying, hey, I successfully received up through byte number 2000.
Which feeds directly into the third service retransmission.
Hmm.
If the sender fires off a chunk of data and doesn't get that acknowledgement back within a really specific calculated time frame, usually measured in just milliseconds, TCP just assumes the data was lost in transit.
And it automatically retransmits it.
Right. But the fourth service is the one that really stood out to me. It's perhaps the most sophisticated: flow control.
Hmm.
Because networks are dynamic, right? Sometimes a receiving computer just gets bogged down.
Yeah, maybe its CPU is busy or its memory is full. And if a sender is blasting data at a gigabit per second and the receiver can only process a megabit per second.
Data gets dropped.
Exactly. So TCP prevents this using a mechanism called the sliding window.
I was reading about this window concept in the notes.
Yeah.
It's brilliant. The receiver doesn't just acknowledge the data, it also sends back a number indicating exactly how much buffer space it has left.
Right. It might say, I received your data, and I currently have a window of 50,000 bytes available. But if the receiver starts getting overwhelmed, that window size shrinks. It might drop down to 10,000 bytes.
And the sender sees that.
It does. The sender sees that shrinking window and mathematically throttles its transmission rate down to match. If the window hits 0, the sender stops completely and just waits for the receiver to catch up.
That is an incredible amount of micromanagement. And obviously, all of this perfection comes with a heavy tax. TCP is what's known as a stateful protocol.
Both the sender and the receiver have to allocate memory and CPU cycles to constantly monitor the exact state of the conversation.
Plus the overhead. To carry all those sequence numbers, acknowledgement numbers, and window sizes, TCP adds 20 bytes of header data to every single segment it transmits. It's heavy, and it requires establishing a formal session before any actual application data can even move.
But for a lot of tasks, you gladly pay that 20-byte overhead tag.
Oh, absolutely. The notes list databases, standard web browsing over HTTP or HTTPS, and email via SMTP. I mean, if you're logging into your bank account, you cannot afford for a single byte of data to go missing or arrive out of order.
A missing 0 in your account balance ruins the entire transaction. You need TCP's absolute reliability there.
Right. But what if you don't? This brings us to the second protocol, UDP, or the User Datagram Protocol.
And UDP is fascinating because it is the exact opposite of everything we just talked about.
It really is.
Yeah.
If TCP is a registered letter, UDP is, well, it's like dropping an unregistered postcard into a corner mailbox, walking away and literally never thinking about it again.
That's spot on. It's connectionless, meaning it doesn't bother establishing a session. It's stateless, meaning neither the sender nor the receiver allocates memory to track the conversation. It simply starts blasting data into the network.
It offers best effort delivery.
Right, which means there are no acknowledgments, no retransmissions, no sequencing, and no flow control.
Okay, let me stop you right there. Because when I first looked at this, I had a really hard time understanding why this even exists. You're describing a protocol that is seemingly designed to lose data.
It does sound counterintuitive.
Right. It throws information into the void and just hopes the network figures it out. Why would any software developer actively choose a protocol that strips away every single safety net?
Well, it all comes down to the brutal reality of latency. Because UDP strips away all of those tracking mechanisms, its header is incredibly lean. It only adds 8 bytes of overhead compared to TCP's 20. But more importantly, it never stops to wait.
Okay, but when does raw speed actually matter more than, receiving all the data?
Think about real-time communications, a voice-over IP phone call or a live video stream. Let's imagine you're on a video call using TCP. You're talking, the video streaming, and somewhere in a router halfway across the country, a tiny packet representing a split second of audio gets dropped due to network congestion.
Okay, so because it's TCP, the receiver realizes a sequence number is missing.
Right. And here is where a mechanism called head-of-line blocking occurs.
Ahead of line blocking.
Yeah. TCP is a perfectionist. It absolutely refuses to hand data to the application out of order. So even if packets number 6, 7, and 8 arrive perfectly fine, TCP holds them hostage in a buffer.
Oh, wow.
It stops the entire video feed, sends a message back to the sender demanding packet number 5 be retransmitted, waits for it to cross the internet again, finally puts it in order, and then resumes playback.
Oh, man. So for a live conversation, you would experience this massive, confusing multi-second freeze just to recover a microscopic syllable from 3 seconds ago.
Exactly, which completely destroys the flow of a live conversation. You don't care about a sound someone made 3 seconds ago. You care about what they're saying right now.
That makes total sense.
With UDP, there is no head-of-line blocking. If a packet drops, UDP doesn't care. It just hands the next packet to the application. You might hear a millisecond blip of static, or a single frame of video might get slightly pixelated, but the stream keeps pushing forward in real time.
So for live multimedia, trying to achieve perfection actually creates a worse user experience than just accepting a little bit of data loss.
Precisely. TCP is for when every byte is sacred, like downloading a file or checking your bank balance. UDP is for when latency is the enemy. Live video, online gaming, or rapid-fire network requests like DNS lookups.
Right, where if a request fails, it's actually faster to just ask again than to wait for a complex retransmission process.
Exactly.
Okay, so we have our two methods of transport, TCP for reliability, UDP for speed. But we still haven't solved how the transport layer actually routes this data to the correct application on your machine. We know it uses multiplexing, but how does the network physically label the traffic?
And this is where port numbers come into play. Every single packet of data, whether it's TCP or UDP, has a source port and a destination port stamped right into its header. It's essentially an addressing system that exists entirely inside your computer.
It's like an apartment building analogy. If the IP address gets the data to the right building, the port number is the specific apartment door. You can't just send a package to the building. You need to know which door to knock on.
That's a great way to conceptualize it. And in networking, we use the concept of a socket. An IP address gets the data across the internet to your specific machine. But your machine has dozens of different services running. The port number identifies the specific service. When you combine an IP address and a port number, you create a socket.
For example, if a server's IP address is 192.168.1.5 and the web service is running on port 80, the socket is those two pieces of data bound together. The network routes to the IP, and the OS networking stack looks at the socket to hand the data to the web server process.
And this whole system isn't just random. The Internet Assigned Numbers Authority, or INA, oversees the port number registry. There are exactly 65,535 possible ports, and they're divided into 3 distinct categories to maintain order.
Right, the first category is the well-known ports, which range from port 0 to 1023. And these are reserved for the universal services that make the Internet actually function.
Yeah, and there's a historical security reason for this. In many operating systems, binding an application to a port below 124 requires root or administrator privileges.
Oh, really?
Yeah, it prevents a malicious user on a shared server from spinning up a fake web server on port 80 and stealing all the traffic.
That's really smart. And the outline gives the classic examples. Unencrypted web traffic always defaults to port 80 for HTTP. Secure web traffic hits port 443 for HTTPS. Email routing uses port 2005 for SMTP, and domain name lookups use port 53 for DNS. So if a client is trying to reach a web server, it inherently knows to aim for port 80 or 443 without having to ask first.
Then the second group covers the registered ports running from 1024 to 49,151. These are assigned by INA to specific companies or applications. Like a database company or a gaming platform might register a specific port in this range, so their software always has a predictable channel to communicate on.
But the third group is where the mechanics get really interesting. The private or dynamic ports, ranging from 49,152 all the way up to 65,535.
Also known as ephemeral ports.
Right. And they are the key to how your computer handles multiple connections to the exact same server.
Right, because think about what happens when you open two different tabs in your browser and go to the exact same website. Both tabs are sending data to the server's destination port 443, but when the server replies, how does your computer know which tab gets which data?
It uses those ephemeral ports. When tab number 1 makes a request, your operating system dynamically grabs an available high port, say 49,152 reach, and assigns it as the source port for that specific conversation. When tab number 2 makes a request, the OS just grabs the next available port, 49,153.
Exactly. The server replies to whatever source port the client used. So the data for tab 1 comes back addressed to port 49,152, and the OS seamlessly routes it to the correct process. And these ephemeral ports are temporary. The second you close the tab, the OS reclaims the port and throws it back into the pool for the next connection.
And there is a fantastic practical way for you listening to see this entire socket system working in real time. If you open up the command line interface or terminal on your computer, you can run a command called netstat, N-E-T-S-T-A-T, which stands for network statistics.
It is an incredibly revealing tool. When you run it, your computer will print out a massive list of every single active network connection bound to your operating system at that exact moment.
It's wild to look at.
Yeah, you'll see a column for the protocol showing whether it's using TCP or UDP. You'll see your local address, which is your IP, appended with that dynamically generated ephemeral port.
And you'll also see the foreign address, showing the IP of the server you're connected to, usually ending in a well-known port like 443. You'll also see the state of the connection, like established or listening.
And this isn't just a neat party trick, it's a fundamental security auditing tool. Because the transport layer usually operates invisibly, malware can easily open a background socket and start exfiltrating data. By running netstat, you strip away that invisibility. If you see an established TCP connection on a strange port communicating with a foreign IP address you don't recognize, it's a massive red flag that a rogue process might be running on your machine.
It literally shows you all the invisible doors open on your network. Now, I want to transition to the actual choreography of how these connections are made, specifically focusing on TCP. Because earlier, we established that TCP requires a formal session before it can send any application data. It uses this mechanism called the three-way handshake.
It's a critical synchronization process. Before a single byte of your web page or email is sent, the client and the server exchange 3 distinct packets. This handshake verifies 3 things: that the destination IP is reachable, that the specific port is actually open and accepting connections, and it synchronizes the sequence numbers both sides will use to track the data.
The 3 steps are pretty elegant. Step 1 is SYN for synchronize. The client sends a SYN packet to the server. It's effectively saying, hey, I want to open a TCP session, and here's my initial sequence number so we can start tracking.
Now, let's pause on that initial sequence number, or ISN, because the source notes highlight a really fascinating security vulnerability here.
Oh, yeah.
In textbooks, we often explain sequence numbers using simple integers. Like the client says, my sequence number is 100, and the server replies, got it, waiting for byte 101. But in modern operating systems, ISNs are heavily mathematically randomized.
But why go through the computational effort of randomizing them?
Because of a vulnerability known as a TCP sequence prediction attack. If an operating system used a predictable counter for its sequence numbers, say just adding one to the last connection it made, a malicious hacker could observe a few connections and easily guess what the very next sequence number is going to be.
Oh, and if they can guess the number, they can impersonate the client.
Exactly. The attacker could blind fire a forged packet at the server containing malicious commands, stamping it with the predicted sequence number and a spoofed IP address. The server receives it, sees the correct sequence number, assumes it's a legitimate piece of data from the established connection, and executes the malicious payload.
That is terrifying.
Yeah, but by heavily randomizing the initial sequence number during this first SYN step, operating systems make it virtually impossible for an attacker to guess the sequence and inject fake packets.
That is a brilliant mechanism to prevent spoofing. Okay, so the client securely sends the SYN. Step 2 is SYN ACK. The server receives the request, processes the randomized ISN, and replies with a packet that has 2 control flags set. It sends an ACK, acknowledging the client's sequence number, and simultaneously sends its own SYN flag, requesting a session in the opposite direction with its own highly randomized initial sequence number.
Which brings us to the final step, the ACK. The client receives the server's SYN, mathematically verifies it, and sends back one final acknowledgment packet. Both sides have now synchronized their counters, the state transitions to established, and the actual transfer of application data can finally begin.
SYN. SYNACK.
Exactly.
But as meticulously as TCP opens a connection, closing it requires even more coordination, because TCP is a full duplex protocol.
And full duplex is a vital concept here. A single TCP connection isn't one pipe, it's two completely independent one-way data streams overlaid on top of each other. The client is sending to the server, and the server is sending to the client, but their sequence numbers and buffers are managed completely separately.
Right.
Because of this, you can't just flip a master switch to close the connection. Each direction must be terminated independently.
This results in a four-way termination process using the FEN or finish flag. And reading through the mechanics of this in the notes, it instantly struck me as the networking equivalent of, like, a polite, stereotypical Midwestern goodbye.
I can totally see the parallel.
Right. When you leave a gathering in the Midwest, you don't just walk out the door. It's a structured, phased process. First, the client decides it has no more data to send. It slaps its knees, stands up, and says, well, I should get going. That's step one, the client sending the FAN flag.
Step 2 is the server receiving that FIN and sending back an ACK. I acknowledge you are done sending. But here is the critical part of full duplex. The server might still have data in its own buffer that it needs to transmit, so the connection enters a half-closed state. The client cannot send any new data, but it must remain open to receive whatever the server has left.
Right. The host is saying, okay, sounds good. Let me just pack up these leftovers for you. The server continues sending data until its buffer is empty. Then, step 3, the server realizes its independent stream is also finished. It sends its own FIN flag. All right, I'm fully done sending data too.
And finally, step 4, the client receives the server's FIN and sends the final ACK. Got it. Acknowledging your FIN, the session is closed.
FIN, ACK, FIN, ACK. 4 discrete steps just to hang up the connection. Both sides have to independently declare they are finished, and both sides must independently acknowledge the other's declaration before the operating systems will clear those sockets from memory and reclaim the ephemeral ports.
It perfectly encapsulates the ethos of TCP. It leaves absolutely nothing to chance. It tracks every byte, secures the connection against spoofing, actively manages network congestion through flow control, and ensures mutual agreement before it shuts down.
Which really brings us back to the big picture of this deep dive. Think about the sheer scale of what we've uncovered. The next time you simply click a link on a web page, consider what happens in the fraction of a millisecond before the screen even changes.
It's massive.
Your operating system grabs a dynamic ephemeral port from the pool. It generates a mathematically randomized sequence number to thwart attackers. It fires off a SYN packet across the globe to initiate a three-way handshake.
The server responds, the session is established, and TCP begins its obsessive tracking process. It slices the incoming HTML and images into segments, monitors sliding flow control windows, buffers out-of-order packets, automatically retransmits anything lost in the ether, and interleaves the resulting data stream with all your other background applications.
And the second the page finishes loading, it executes that polite four-way FIN ACK goodbye to release the resources. All of that invisible, hyper-complex logic happens before you even have time to blink. The transport layer takes the chaotic, unpredictable void of the raw internet and molds it into the seamless, reliable utility we rely on every day.
It truly is a masterpiece of distributed engineering.
But I want to leave you, the listener, with a final thought to ponder. A challenge that builds on the fundamental tension we explored today between TCP and UDP. We've established that TCP gives us absolute mathematical reliability at the heavy cost of overhead and delays. And UDP gives us blazing instantaneous speed by stripping away all those guarantees. It's the classic engineering trade-off, you know. You can have it perfect or you can have it fast.
But the future of technology isn't really going to accept that compromise.
Exactly. Look at where we're heading. Remote robotic surgery, where a specialist in New York is manipulating a scalpel inside a patient in Tokyo. Or highly immersive, hyper-realistic virtual reality environments where physical motion is tied directly to network feedback.
Yeah, in those emerging scenarios, you absolutely cannot afford a single dropped packet, which means you desperately need TCP's perfection. But you also cannot afford a 200 millisecond delay while a lost packet is retransmitted, which means you desperately need UDP's zero latency speed.
The next generation of applications requires both absolute perfection and zero delay simultaneously.
It's a huge hurdle.
So the question is, how will the Internet's transport layer adapt? How do you engineer a protocol that provides the ironclad guarantees of a registered letter but delivers it with the unburdened speed of a postcard? When the network is asked to drive a Formula One car at top speed while balancing a house of cards on the steering wheel, how will it pull it off? It's something to think about the next time you drop a piece of data into the network.